look at the commutators of LZ and L plus and L minus, and also of L squared. We have L squared commutator with L plus and L minus. Well, that would be equal to commutator of L squared with Lx plus or minus I commutator of L squared with Ly. But what are those two commutators equal to? Well, we said the commutator of L squared with Lz was 0. They have simultaneous eigenvectors. And then we said, and it has to be true, therefore, that L squared and Lx have a commutator of 0, 2. If Lz commutes with L squared, so must Lx, so must Ly, because what we call the x, y, and z axis is completely arbitrary. So it has to be true that those are both 0. So L squared commutes with L plus and L minus. More interesting, however, is what does Lz do? Is Lz willing to carpool with L plus and L minus, or are they like, nope, don't get along, sorry, ain't gonna happen? Well, that'll be the commutator of Lz and Lx plus or minus I times the commutator of Lz with Ly, just from the definitions of what L minus and L plus are. So, plus or minus I commutator of Lz with Ly. But the commutator of Lz and Lx is IH bar Ly. That's one of the cyclic permutations that produces a plus sign. So we get IH bar Ly for the first term, plus or minus I, and the commutator of Lz and Ly, that's one of the ones that comes with a minus sign instead. So the commutator of Lz with Ly is minus IH bar Lx. So this turns into plus or minus H bar times Lx plus or minus I Ly. Just factoring away here. So in other words, this is going to be, for the Lx term, I've got plus or minus I times minus I. Well, I times minus I is 1. So I get plus or minus H bar Lx for the Lx term. And then for this term, I've got IH bar Ly. And so this would be plus ILY or minus ILY, which is both plus ILY. So IH bar Ly, so that doesn't change anything. So that's plus or minus H bar times what? What is Lx plus or minus ILY? What is Lx plus or minus ILY? Yeah, it's the raising or lowering operator in that order. L, this is plus or minus H bar, L plus or minus. Right? This is we're making a choice here. You know, the order of the subscripts is important. So we're saying the commutator of Lz, this is equivalent to commutator of Lz with L plus is H bar L plus. Commutator of Lz with L minus is minus H bar L minus. This is equivalent to those two statements. That's what the order means. So just to be clear on that, Lz, L plus, commutator is H bar L plus, Lz, L minus, commutator is minus H bar L minus. So they don't get along, they do not carpool with one another. Apparently, if they try to carpool with one another, L plus kills LZ, and that's all that's left in the car. And if LZ tries to carpool with L minus, then apparently there's more of a struggle. LZ still gets killed, but it's a bigger fight, and so L minus gets turned over upside down in the end. So L minus is apparently, LZ apparently, L minus is apparently a little weaker, because LZ at least struggles more and flips him or her upside down when they're struggling in the car. Alright. Well, what does that PHYS? That PHYS us a lot. Because what it says is that, as we'll see, L plus and L minus play roles similar, as we mentioned, to A plus and A, for A plus and A minus for the harmonic oscillator. So let's apply LZ to L plus applied to eigenket alpha beta. Well, if we go back to the commutator, if it's true that LZ L plus is H bar L plus, that says that LZ L plus minus L plus LZ is H bar L plus. So that says that LZ L plus is the same thing as L plus LZ plus H bar L plus, and that's what we're about to use. Commutator of LZ and L plus is H bar L plus. Commutator says LZ L plus minus L plus LZ is H bar L plus. So now that says LZ L plus is, take the L plus LZ to the other side, L plus LZ plus H bar L plus. L plus LZ plus H bar L plus. L plus LZ plus H bar L plus. So let's write that. So LZ on L plus alpha beta is the operator L plus LZ plus H bar L plus applied to eigenket alpha beta. What is LZ operating on alpha beta? What does that produce? LZ on alpha beta gives, what do those labels mean? Beta is the what? Yeah, but right now though we're pretending we don't know that. We're letting alpha and beta just be thingies. And we're going to show that they have those forms that we claim later. So you don't get to use the final result in the middle, right? So, true, but not allowed yet, okay? So, beta is the eigenvalue of L sub z. So by definition, this is beta times alpha beta. Remember, alpha and beta are just labels. They label the eigenvalues of L squared and LZ. So this turns into L plus times beta, which is simply a number, the eigenvalue, plus H bar times L plus but beta and h bar are just numbers. And they are both multiplied by L plus, so I get to factor them out. This factors into beta plus h bar multiplied by L plus alpha beta. So, what does that say? That says that L plus alpha beta is an eigenket of LZ with an eigenvalue beta plus h bar. In other words, L plus alpha beta has a z component of angular momentum which is h bar greater than alpha beta itself does. Right, see the logic there? LZ on alpha beta gives beta times alpha beta, so it has beta as its amount of z component of angular momentum. So if I apply LZ to L plus alpha beta, I get L plus alpha beta back multiplied by beta plus h bar. So it's also an eigenvalue, an eigenvector of LZ, but its eigenvalue is h bar greater than the eigenvalue associated with alpha beta. L plus alpha beta is also an eigenket of LZ, but with eigenvalue beta plus h bar instead of just beta. So I have raised the z component of angular momentum by h bar when I kick alpha beta with L plus. That's similar to where we found that if we apply the raising operator to an eigenstate of the harmonic oscillator, it raises the energy by h bar omega. Here, we're raising the angular momentum, z component, by h bar. So a very similar kind of thing. Meanwhile, back at the ranch, what if I hit that same cat L plus alpha beta with L squared instead of L sub z? Well, what do we know about L squared and L plus? Will they carpool? Do they get along? They do, yes, they carpool. They commute with each other. So this is the same thing as L plus L squared alpha beta. I can flip the order around because they commute with each other. But L squared applied to alpha beta produces what? I don't need those parentheses. I'm just putting it in there to say, let's think of this thing as an object here. What's L squared applied to alpha beta? Alpha times alpha beta, because alpha is the eigenvalue of L squared, because that's what we were just saying. Alpha is the eigenvalue of L squared. So this is going to be equal to alpha times L plus alpha beta, the ket that we started with. So L plus alpha beta, that ket, is an eigenket of L squared, which also has eigenvalue alpha. The eigenvalue of L squared isn't changed by smacking alpha So L plus leaves alpha alone, but raises beta by h bar. That's what L plus does. It makes a new state where the z component of the angular momentum hops up by h bar, whereas the total angular momentum squared doesn't go anywhere. So go back to something quasi-familiar, go back to hydrogen. What we're saying is that if I have a state that is some psi NLM, then if I hit that with L plus, I'm going to get some number, because remember there's going to be some normalization involved, some number times psi sub n L m plus 1. M went up by 1, L didn't do anything. So in other words, what we're doing is L plus, you have a set of the states that have a certain value of L, and then M ranges from minus L to L. What L plus does is it takes states in that set and moves them up the ladder, so to speak. In other words, L equals 2, M equals 0. If you hit it with L plus, you get a multiple of L equals 2, M equals 1. And if you hit it again, you'll get L equals 2, M equals 2. And if you hit it again, what will happen? Is there such a thing as L equals 2, M equals 3? No, that can't happen. So we're going to say, oh, eventually this has to stop. And we haven't gotten there yet, but we're going to say eventually this has to stop. This can't go on forever. In fact, the fact that it has to stop is what's going to convince us that M actually has to be an integer that lies between, that M has to make steps that lie between minus L and plus L. But then we're going to discover that actually L can be a half integer, in which case it represents spin instead of orbital angular momentum. But again, we're not there yet. This sort of just like, where is this headed? Let me peer through the fog. This is where this is headed. We're not there yet, but keep on driving, and we'll eventually get there. Okay? So, any questions? Similarly, I'm sorry, don't say that yet. Say it in a second. Sorry about that. So, what we can conclude then is that L plus on a state alpha beta is equal to, I'm going to call it C sub plus of alpha and beta times alpha comma beta plus h bar. So in other words, what we're saying is, if I hit alpha beta ket with L plus, I get a ket where the value of alpha is the same, but as we said before, the LZ eigenvalue increases by h bar. So the new value of beta is the old beta plus h bar. We've raised the z component of the angular momentum by h bar. We've left L squared alone. We've left the total angular momentum squared alone. And this is some constant. And if you're like, what? How come there's a constant? I'll remind you, we've run into that before. We've run into, remember that, what is A plus applied to n? It's not just n plus 1, it's the square root of n plus 1 times n plus 1, right? And A minus applied to n is the square root of n times n minus 1. Well, this C plus is something to be determined. We haven't determined it yet, but all we know is that L plus of alpha beta is some multiple of this ket. And the idea would be we can choose this to make sure that if this is normalized, then the result is also normalized. We got this root n plus 1 and root n by saying, I want the new state to also be normalized. So this is the same deal. If I insist that this state be normalized, then there's some constant out front that works out not to be 1, just like it happened for the harmonic oscillator. We haven't figured out what this is yet, but that's the point. And remember that if I have an eigenvector of some operator, if I have an eigenvector, most general thing we can say here is that the new eigenvector is some multiple of the normalized eigenvector alpha beta plus h bar. There has to be, the most general relation is it's some number times the new normalized eigenvector. And we'll have to figure out what c plus of alpha beta is that would preserve the normalization. We haven't done it yet, but it's not important to do that yet. Okay, any questions? Now here's where I get to say similarly. If you do the same business with L minus, apply that to alpha beta, then you get some constant, which we'll call c minus as a function of alpha and beta, times alpha, comma, what do you think will go after the comma? Instead of beta plus h bar, we get beta minus h bar. Yep. And you show it the same way we did before. You write that if I hit this with LZ, LZ L minus is L minus LZ minus H bar L minus times the eigenket. And so before we had an L plus LZ plus beta H bar. This time we would have an L plus LZ minus by beta H bar, and that's why there shows up with a minus sign here instead of a plus sign there. So L minus lowers the angular momentum by H bar, the Z component. L plus raises it. So, put it all together. This implies that given a state, alpha beta, there exist states alpha comma beta plus H bar, alpha comma beta plus 2H bar, etc., and alpha comma beta minus H bar, alpha comma beta minus 2H bar, dot, 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 which are obtained by repeatedly applying L plus or repeatedly applying L minus. So we've got a family of states which have higher LZ and a family of states which have lower LZ, all in increments of H bar. Now, by going to the coordinate basis, we already saw that for orbital angular momentum it ought to be true that the LZ values differ by H bar. Here we've seen it. Notice that here we never wrote down, we started fresh and just said beta, and we never wrote down a differential equation. It was all just the commutation relations that led to LZ, that led to L plus and L minus having these properties. So purely from the commutation relations, amazingly enough, we've deduced that the allowed values of L sub Z are a family that differ by steps of H bar from one another. Questions, comments, observations? Ben's thinking, yeah, oh man, this is cool. Right? I can see it in your eyes. Yes, give me the thumbs up there. Okay, so, problem. In large or small? Because at first it looks like we do that. Just keep L plus forever. L plus, L plus, L plus. Hit it a million times. We've increased LZ by a million H bar. Hit it with L minus a million times. LZ is decreased by a million H bar. If LZ can be arbitrarily large or small, well, that would lead to something that would be interesting. It would seem we could have LZ squared was greater than L squared, was greater than the square of the angular momentum total there. In other words, we could get a situation where the total angular momentum would be smaller than one of its components. And that's like saying, so, what's your component of velocity in the north direction? 100 miles an hour. What's your speedometer reading? 10 miles an hour. Now, quantum mechanics is weird, so you might be tempted to say, well, it's quantum mechanics, so what the hell? But quantum mechanics isn't that weird. It doesn't produce that situation. So we would like to discover that that doesn't happen. And in fact, we will discover that that cannot happen, and that will make us happy. However, there is a limit to how much you can raise or lower LZ. Because, consider the following. Take this inner product. Alpha beta inner product L squared minus LZ squared alpha beta. So sandwich L squared minus LZ squared between pet alpha beta and raw alpha beta. So these are the operators here, the abstract operators that are being thrown in the middle there. And as an operator, not just, I'm not talking numbers, as an operator, L squared is Lx squared plus Ly squared plus Lc squared. The operator is Lx squared plus Ly squared plus Lz squared. So L squared minus Lz squared is the operator Lx squared plus Ly squared. What does a sandwich like this represent? It's an expectation value, right? This is for state alpha beta. What's the expectation value of L squared minus Lz squared? Well, it's equal to the expectation value of Lx squared plus Ly squared. But Lx squared and Ly squared, it's going to be some weighted sum over the eigenvalues of Lx squared and Ly squared. Because I could write these alpha betas as superpositions of the eigenstates of this operator right here. And so this is positive definite. All the eigenvalues of those operators are greater than 0. There's no way the expectation value of the sum of the squares of the x and y components of angular momentum could be negative. Again, quantum mechanics is weird, but isn't that weird? That can't happen. Oh, but wait a minute. is L squared on alpha beta? L squared on alpha beta is an eigenket of L squared, right? So L squared on alpha beta is alpha times alpha beta, right? And LZ on alpha beta is beta times alpha beta. So LZ squared on alpha beta is beta squared times alpha beta, right? If I apply LZ to alpha beta twice, I'm going to get beta times alpha beta. So here, I just get the simple numbers, alpha minus beta squared, in that delicious sandwich. So this says that the simple number, alpha minus beta squared, times the inner product of alpha beta with itself, has to be greater than or equal to 0. That's because that expectation value over there has to be positive definite. Positive definite means greater than or equal to 0. What's that?
If it's positive definite, is it going to be just bigger than 0?
It means greater than or equal to 0 because, in principle, well, there is a state. There is the state where alpha and beta are both 0. Where there's no orbital angular momentum, and therefore there's no z or x or y component. They're all 0. So there is a lowest state of angular momentum where alpha and beta are both 0. So this could be 0, but it can't. It can't. Positive definite means it can't be less than 0, but it might be 0. So positive definite means greater than. Yeah. So actually, this is a goof. This is supposed to say greater than or equal to 0. Yeah, because that's what we need to avoid. Certainly, a vector squared can be easy. That's fine. And what is this inner product right here if we've bothered to normalize our eigenkets? 1. Yeah. That's equal to 1. If we've normalized the eigenkets, it's just equal. It's 11. If we've normalized the eigenkets, that's equal to 1. So this says that alpha is greater than or equal to beta squared. Well, that's happy because alpha represents the total angular momentum squared. Beta represents the z component. So this says the total angular momentum squared has to be greater than or equal to the z component of the angular momentum squared. That has to be true. That if you're in an eigenstate, that looks like an operator relation right there. But in other words, if you let L squared be the total angular momentum squared for some eigenstate, it has to be greater than or equal to the z component of the angular momentum squared if you've got a simultaneous eigenstate. So in other words, yeah, quantum's weird, but it's not that weird. And again, notice all this just came from operator considerations. It wasn't just, gosh, that would be really weird. I mean, no, we showed that doesn't happen. So quantum mechanics is weird, but not infinitely weird. Infinitely weird, we'd be in this rule world that's infinitely weird, right? And so, it'd be like, of course we're all changing colors during this conversation. And of course it makes sense when I'm going, and you guys would be like perfectly understanding it, so it's not that weird, right? We know the world makes sense on some level. No, it doesn't. But whatever, we can pretend it makes sense. Yes, it does. I was a bad physicist to say that. All right, so since beta squared is bounded by alpha, can't get bigger than alpha, there must exist a state which we will call alpha beta max. So you guys are maybe too young to remember that there used to be VCRs that were called beta maxes. So anyway, yeah, VCRs were these machines you put tapes in, and you could videotape shows. Anyway, you guys know what VCRs are. Your kids won't, but you guys know what VCRs are, right? You know what VCRs are, right? Yeah, okay. Yeah.
I still have my Disney movies on VHS.
Do you really? Oh yeah, right. Yep, very good. Yeah, I still got a videotape collection.
Again, so it's Star Wars on Betamax.
Oh really? Wow, okay, there you go. Betamax was a superior format in terms of the picture quality. However, you could only store 90 minutes in high quality mode on a tape instead of 2 hours. So even though the quality was higher than VHS, VHS won the format war because people were more interested in recording more than in recording better. And so it's not true that the desktop technology always wins. Another example would be there are many more Windows PCs in the world than there are Macintosh computers. That's not because Windows is a superior operating system, especially in the past. I mean, it used to be just hands down. Windows 7 isn't too bad, but in the past it used to be like a Ferrari versus, a Yugo or something like that. And yet still the Yugo, because it was cheaper, sold more, essentially. Anyway, the thing is though, the difference between Bill Gates and Steve Jobs is not that much. Steve Jobs would be Bill Gates because Steve Jobs would like to have everybody having to buy his stuff. He's just as bad as Bill Gates is as far as that's concerned. He wants to control the world too. It's just that Bill Gates actually managed to do it.
So, in other words, arrogance is about equal.
Oh yeah, they have
But
comparable
one
arrogance.
is
They're both kind of jerks.
But one is slightly more.
But one has more creative people. One is a lot more creative. The other one just like clones stuff. But then if you guys heard the joke, what's the difference? So that's the difference. There is no real difference between Bill Gates and Steve Jobs on that level. But what's the difference between God and Bill Gates?
I could name quite a million of them, but
The difference is that God does not think that he is Bill Gates.
yes, of course. That's the main difference.
Yeah. All right. So anyway, which cannot be replaced. After all that. So L plus applied to alpha beta max gives 0. Stops the chain. L plus usually raises people, but it kills this one. Goes away. So then you can keep applying L plus to 0, and you get 0, 0, 0, 0, 0, 0, so you're not going anywhere anymore. So that would mean, well, I could hit it without minus and still get 0. I could hit it with fret and still get 0, but L minus could be in there. So L minus L plus alpha beta max is also 0 because anything applied to that is 0. Oh, but wait, there's more. But L minus L plus is equal to Lx minus I Ly, Lx plus Li Ly. But now we can expand that sucker out. That's equal to Lx squared plus Ly squared plus I times Lx Ly minus Ly Lx. So that's just expanding all that out. You're going to get Lx Lx and then a term which is plus ILY times minus ILY, and I times minus I is 1, so you'll get plus Ly squared. And then you've got the cross terms where, again, order is important, and so Lx Ly is multiplied by plus I, and Ly Lx is multiplied by minus I. But wait a minute. Lx squared plus Ly squared is also known as L squared minus Lz squared. And LXLY minus LYLX is also known as LXLY minus LYLX is, just tell me what it is without saying what it is yet, so to speak. In other words, AB minus BA is also called the commutator, yeah. This is the commutator, LX comma LY. But the commutator of LX and LY is, no, IH bar LZ. That's right, it's IH bar LZ. Yes, IH bar LZ. So this turns into L squared minus LZ squared plus I times IH for LZ, and so that turns into minus H bar L sub Z. So L minus times L plus is the same thing as L squared minus LZ squared minus H bar LZ. So that says that L minus L plus alpha beta max equals 0 is the same thing as L squared minus LZ squared minus H bar LZ applied to alpha beta max is equal to 0. But alpha beta max is an eigencat of all of those three operators. What is L squared applied to alpha beta max? It's alpha times alpha beta max, because alpha is the eigenvalue of L squared. What is LZ squared applied to alpha beta max? Beta max squared, alpha beta max, so we get minus beta max squared, and then we get minus H bar beta max. Alpha beta max equals 0, which means that the thing in parentheses has to be 0, because the thing not in parentheses, alpha beta max, isn't 0. So the thing in parentheses has to be 0. So the stuff in parentheses has to be 0, or in other words, that says that alpha is equal to beta max times beta max plus H bar. Alpha is beta max times beta max plus H bar. We can go the other direction too. Yeah, actually, no, that would be a good place to start next time. So we're gonna say, okay, well then there must also be some state alpha beta min that L minus kills, and then we'll say what's L plus L minus alpha beta min. Similar considerations will say that alpha has to be equal to beta min times beta min minus H bar, and that's going to say that beta max has to be minus beta min, and that's going to say, oh, symmetric states going from plus some maximum to minus some maximum. But then we're going to discover too that you can get half integer values for the angular momentum. And again, it's like this clue that the angular momentum commutations themselves imply the existence of the possibility of angular momentum that can't be accounted for with orbital angular momentum. There will be spin angular momentum. And we're going to see the way that you handle that is you make your wave function have multiple components. You make your wave function be a spatial part times a column by matrices, which represent spin angular momentum operators. And so then you'll find, you see, kind of, how do you actually write down what the spin part of the wave function is? You do that by including a column vector of spin components, so to speak, of spin wave function components, which right now is very abstract, but it's going to get really concrete for you. Solid. Something to look forward to.